me today, and he will tell us about the Nielsen realization problem for untwisted automorphisms.
All right. Thank you for the invitation. I've really enjoyed the conference so far. Lots of smoked salmon and lots of just plain smoke. So this is joint work with Ruth Charney and Karen Vogtmann. And as Ruth told you yesterday, this is going to be a sort of follow-up to what she talked about. So we're going to be studying automorphisms of right-angled Artin groups, and in particular, their finite subgroups. So let me start off by defining gamma is our defining graph. It's going to be a finite simple graph. And then A gamma will be the associated right-angled Artin group. And I'm going to start off with recalling what Ruth told us yesterday. So there exists a finite-dimensional contractible space O gamma on which the outer automorphism group out of A gamma acts with finite stabilizers. And what I want to sort of dig into today is a little bit more about how this space is defined, and in particular, how to understand these finite stabilizers. So that'll be about finite subgroups of out of A gamma. So the space, it's not just a space that out of A gamma acts on. We know what the points look like inside of it. So points in our O gamma are pairs XH, where X is a locally cat zero space, and H is some homotopy equivalence from our space X to the Salvetti complex. So this is a marking. It identifies the fundamental group of our X with A gamma. And of course, we didn't allow all locally cat zero spaces that do this. We had to restrict our metrics. But there's also an equivalence relation on these pairs. So we say that XH is equivalent to X prime H prime if there exists an isometry, say I, from X to X prime that sort of commutes with the markings up to homotopy. So I have X here, I have X prime, and I've got my isometry between them. And then I can send X to the Salvetti. And I also have the marking that sends X prime to Salvetti. And if this diagram commutes up to homotopy, then we say they're the same point. Okay, this is a pretty standard construction. This is what you do in Teichmuller space, for example. But this is very important, especially for understanding stabilizers. So let me just recall also how out of A gamma acts on this space. So out of A gamma acts on O gamma on the left. And the way that works is you take out of A gamma, and since the Salvetti is a Ka gamma 1, you can identify this with the group of self-homotopy equivalences of the Salvetti. So if I take some automorphism in here, I can represent that as a map from the Salvetti to itself. So I take some F that represents the homotopy class of this phi under this identification here. And then phi acting on a pair XH is just post-composition with this F. So X, F composed with H. And since my equivalence relation is always up to homotopy, this is a well-defined action. Okay, so that's how the group acts. And what we observe, though, is that if I just have an isometry from X to itself, I can send X to the Salvetti by a marking. I can also send X to itself by the isometry, and then I can also recompose with the marking. And now I know I can fill this in some way by some element in the outer automorphism group. And so if we go this way around the square, we see that we just have phi acting on xh, and this is equal to x, where the marking I've used is h precomposed with I. But based on our equivalence, this differs from xh just by an isometry. So this is the same point as xh. And so this tells us that there's this map from the isometry group of X, and it turns out to be surjective onto the stabilizer of this point XH in outer space. Now this is sits inside of out of A gamma, so it's discrete. And so then this map factors through the group of connected components of the isometry group. And so it turns out something you can show is that the stabilizer of XH is exactly the group of connected components. So in general, for these X's, they're sufficiently nice that the isometry group is a Lie group with finitely many connected components. And the connected component of the identity is a torus. It's of dimension equal to whatever the rank of the center is. And so it's just the Clifford translations modded out by the A gamma. But those are obviously sort of don't do anything to pi 1. And those are the only things that really don't do anything to pi 1. Okay. Okay, so this says that whenever at any point in the space, the connected components of the isometry group will give us a finite subgroup of out of A gamma. And the sort of converse to this is what the Nielsen realization problem is about. So Nielsen realization would ask, suppose I give you some finite subgroup F in out of A gamma. Can I find, or does there exist some XH in the outer space such that F is contained in the stabilizer of XH? Okay, so can I realize it as a group of isometries? And equivalently, does F acting on outer space have a fixed point? So that's the basic question we want to answer, and it's just understanding the finite subgroups. So let me give you sort of two motivations for why you might care about this. One thing is that they both hold for free groups and free abelian groups, or at least for their automorphisms groups. And I'll give you a proof of that soon. And so we'd like it to also be true for out of A gamma. And they also hold, I guess, for Teichmüller space as well. And that's where the sort of moniker Nielsen realization comes from. It's an old problem from, I guess, the 20s or something like that. And then it was solved by Kirchhoff in the 80s. So finite subgroup of the mapping class group, there's a hyperbolic surface that realizes that group as a group of isometries. But sort of group theoretic reason why you might care about this is you might want to know, does out of A gamma have finitely many conjugacy classes of finite subgroups? So something like this solution to the Nielsen realization problem together with some sort of co-compactness would allow you to deduce this. And we'll see an example of this later today. And the second thing you might be interested in is, and something we're interested in, is this outer space an E underbar G or an E underbar out of A gamma? So what does this mean? Out of A gamma has torsion, so you can't find a finite dimensional classifying space for it. But that's for, when you talk about a K A gamma 1, that means, or a K out of A gamma 1, that means free actions. And here we're interested in a classifying space for proper actions. So that's what this indicates. And this is connected to the existence of such a thing is connected to lots of conjectures in group theory. What we need to show is not only that the fixed sets of finite subgroups are non-empty, but also that they're contractible. So we need to show that contractible fixed sets. Again, this is something that is true for out Fn. It's true for GLNZ. We'll actually see the proof of that. It's also true for mapping class groups. And so these are really nice, like sort of best, this would say this O gamma is sort of best possible, best thing you could possibly hope for. So, okay, questions? Because you can't find a finite dimensional classifying space, but you can find a finite dimensional one that has this property. That's all.
And all you need to show is contractible spaces, and that's
No, so it's contractible, but yeah, that's what that would do it. Yeah, and yeah, these things are defined up to homotopy equivalence, yada yada yada. I mean, this is a particularly nice one. Yeah. Okay. So right. So let me talk about how to solve the Nielsen realization problem for GLNZ and for out Fn. The proofs are very different. So as we saw yesterday, when you build this outer space, you have to sort of leverage properties of GLNZ and also properties of out Fn. And so any sort of solution to this will also involve that kind of juggling. Okay. Right. So the GLNZ case is classical. And the O gamma in this case is what I'll call Qn. It's this set of positive definite symmetric matrices over R. Okay. If you don't like that, you can also think of this as a symmetric space, or at least a homogeneous space, GLNR mod ONR. And this is how Ruth described it yesterday. But this is just some subset of R to the n choose 2, because it's symmetric matrices. And it turns out that it's a cone. So you can take convex combinations of positive definite symmetric matrices and get positive definite symmetric matrices. But in particular, it's contractible. And so if I take some finite subgroup in GLNZ, and I take some point in this Qn, GLNZ acts on this, and when I look at the orbit, it'll have a fixed barycenter. You can sort of just average. And that will be my fixed point. Okay. So this is like very nice thing. We're sort of exploiting the non-positive curvature here. Again, this thing also admits a metric of non-positive curvature, or at least the SLNR one does. But but this is a very nice proof, and it also gives us the E under bar G thing. If you have two fixed points, then there's a unique geodesic between them. It also has to get fixed by the action. So, okay. So this one we're really using the geometry, but something different happens in the case of out Fn. So this is due to independently to color, Kromsov and Zimmerman in the 80s. And let me start off. The starting point is to look at the following exact sequence. So since Fn has trivial center, this is just the inner automorphisms including in there. So if I take some finite subgroup in out Fn, I can pull it back to aught, and I'm going to get some extension of the free group by a finite group. Okay, and so this E is virtually free. And in particular, there's this result of Karas, Piotrowski, ski solitar, it says that E will act on a tree, T say, with finite vertex and edge groups. And so in particular, the Fn part of E has to act freely. So when I act on it by Fn, this is just some graph of rank n. And F sits inside of the, you get an induced action of F on this, and it sits inside of the automorphisms of G. Okay, so you might be thinking like, okay, how does this correspond to a point in outer space? Well, certainly the graph is in outer space, but what's the marking? Well, I have an action actually of Fn on the universal cover, which is this tree, and that's equivalent to giving a marking. So, so this really does define a point in outer space. So what's the point here? In this case, we're using the geometry of outer space. In this case, we're really using some group theory and some geometric group theory techniques. What I'm going to talk about today is realizing finite subgroups that come from the sort of free part. Okay, and so the techniques are going to be like this. Okay, so let me remind you what the untwisted automorphisms of the right-angled Artin group are. Yeah. Sorry? Oh, I was thinking like, yeah, I guess so. Yeah. But I was thinking like unit length edges or something like that is enough, because we just have this simplicial acting on a simplicial tree, right? So you can just assume all the edges have length 1, for example. Yeah. Right. That's what you would really need. Yes. Yeah. Right. Good. Okay. Right. So the untwisted automorphisms. I'll just remind you. So the automorphisms come from what are called the Lorentz and Servatius generators. And they have sort of several different types. So there's the graph automorphisms. That's just automorphisms of your defining graph. There's the inversions. So these look like V goes to V inverse. There are partial conjugations. So you have your graph, and here's a vertex in it, and this is the star of V. So these are all the things that commute with V. But outside of this, there might be several connected components. C3. And so when you delete the star, you see these different connected components, and a partial conjugation just takes one of them and conjugates everything in it by V. Okay, and since they don't interact with one another, this is defines an automorphism. If you were to conjugate all of them, you would get something that's inner, but just doing one is something non-trivial in out. And then there are sort of transvections. And these fall into two different types, but they always have the form V goes to VW. So what you need in order for this to work is that the link of V, everything that V commutes with, W has to also commute with. And there's two ways this can happen. One way is if you have what's called a fold, and that's when the link of V is contained in the link of W. So V and W in this case don't commute. And then the other way this can happen is if you have what's called a twist, and that's when the star of V is contained in the star of W. And in this case, V and W do commute with one another. So I'll indicate this. These are sort of defining a partial ordering. and I'll indicate this one by V is F less than W, and this one by V is T less than W. Okay. So the untwisted automorphisms are sort of the bulk of all the automorphisms we've defined here. So this is U of A gamma. And then this remaining part are called the twist subgroup T of A gamma. This may come up later on, depending on how much time I have. But what I want to focus on today actually is this part, which is we're just going to take U of A gamma, but ignore the graph automorphisms. Graph automorphisms are kind of annoying. So this is what's called U0. And we'll be realizing finite subgroups in U0 of A gamma. Okay. So, right, I can state the theorem now. So let's say let F inside of U0 of A gamma be finite. Then there exists a point X H in O gamma such that F is contained in the stabilizer of XH. Okay. Let me say a little bit more about this. We actually do something slightly different. So recall that Charney, Samba, and Vogtmann had constructed a space finite-dimensional contractible K gamma on which this untwisted group acts. U of A gamma acts. Okay, and this thing is again capturing somehow the free part. You know, all these automorphisms involve generators that don't commute with one another. So it looks a lot like the spine of outer space. But now inside of here, points are pairs X, and I'm going to distinguish the marking as F, where X is now an NPC cube complex, and F is a homotopy equivalence to the Salvetti, but it has to have a specific form. So since we have the cube complex structure, we have these hyperplanes, and we can collapse some of them to get back down to the Salvetti. And the marking has to play nicely with that. So it has to be the case that when you take a homotopy inverse for that collapse map and then compose it with F, you end up in U of A gamma. Okay, so these are so-called untwisted markings. And that only makes sense when you have this cube complex structure. Right, and the spaces we consider are these what I'll call gamma blowups. So there's a restricted class of these cube complexes that you care about. But in this case, the automorphisms or the stabilizers of some point is actually the automorphism of your cube complex. So the stabilizers act by cubical isometries. Okay. And so what we really prove is that we find a fixed point in here. So in fact, so we'll show that if F is in 0 of A gamma, then F acting on this K gamma has a fixed point. So we're actually getting a cube complex, an NPC cube complex, whose fundamental group is A gamma, and F is acting by cubical automorphisms. Right, so a corollary of this is that U0 of A gamma has finitely many conjugacy classes of finite subgroups. And again, the point here is that we get this Nielsen realization, but this action of U of A gamma on K gamma is co-compact. This U0 is just finite index. That's going to tell us that there's only finitely many conjugacy classes here. Yeah.
You can just explain again what it means the rest, right?
Here.
Yes.
Oh, so I just wanted to distinguish between O gamma and K gamma. So this is the stabilizer of a point in this space, K gamma, is the group of cubical automorphisms of my point X.
So that's a stabilizer in U0.
Yeah. Oh, I guess. Okay. Right. Yeah. Just U of A gamma. Yeah. Right. That.
Okay.
Yeah. Okay. Yeah. Right. All right. Other questions? Sorry. Okay. Right. So this is a sort of like you need some compactness, but then that allows you to say there's only finitely many conjugacy classes. And before I discuss sort of the ideas in the proof, I'll just make a remark. So Hensel and Keelak in previous work, they construct an NPC cube complex, realizing any F finite subgroup of U0 of A gamma. So it's a very long and technical paper. And the cube complex they construct is sort of, it doesn't exist in an outer space, or at least not obviously. So there are lots of interesting ideas in the paper, and some of them we actually ended up using. But because there's no sort of outer space around, it's not exactly clear what this tells you. But it's still an interesting work, so I thought I should mention it. Okay. Right. So in the rest of the talk, I want to talk about the sort of proof strategy here, because I think it's pretty robust and can lead to other results for understanding U of A gamma. So, so I want to tell you about U0 invariant subgroups. Actually, subgraphs. So what's the definition? I look at a subgraph in gamma, and it will be U0 invariant if phi of the corresponding special subgroup phi of A delta is conjugate to A delta for every phi in U0. Okay. So you act on A delta by some automorphism, and it just takes it to a conjugate of A delta, so some other parabolic subgroup. And what this gives you is a restriction mapping from U0 of A gamma to U0 of A delta. Okay, so any automorphism I do acts on A delta, and it sends it just to a conjugate. So all we're recording here is what's happening like inside the subgroup, basically. But what this means is that if I have a finite subgroup here, then I get a finite subgroup here. So this sort of suggests a strategy for realizing finite subgroups if I can sort of realize them on these finite, these U0 invariant subgroups, and then build up my blow up in some way. And so first of all, in order to do that, there have to be lots of U0 invariant subgroups. And so that's what I'm going to show you now. There are lots of them. So maybe the simplest construction is if I take any subset of gamma. And I define the link of E to be the intersection of the links of all the elements in E. So these are all the things in gamma that commute with every single element of E. Well, then link of E is U0 invariant. And of course, this intersection might be empty, but in many important cases, it's not. So for example, the link of any generator is U0 invariant. And also the double link or the link of the link is U0 invariant. And this is just all the vertices, all the W's, such that W is fold bigger than V. So all the things that can fold onto V is the double link. And then there's the triple link. No, I'm joking. I'm joking. Okay. Right. So what else is true about U0 invariant subgraphs is I can take intersections. So if delta 1 and delta 2 U0 invariant, then so is their intersection. And the last example I'll tell you is that if gamma is maybe disconnected and sigma is a connected component, which is not a singleton, not a single vertex, then sigma is also U0 invariant. So there are, in fact, lots of these things. And again, the idea is to sort of use these restriction maps and realize the finite subgroup on pieces and then sort of cobble together a blowup for the whole space. So I'm not going to tell you how to construct blowups, but I'm going to give you several recipes or 2 recipes. If you know how to construct it for some pieces, then you can make a blowup for the whole thing. Okay, so let me show you how to do that. There's sort of 2 cases. The first is if you have a join. So let's say delta is a join of 2 subgraphs. So everything in delta 1 commutes with everything in delta 2. And I want to assume here, for reasons that will become clear, that the delta is U0 invariant. So then delta 1 and delta 2 are also U0 invariant because delta 1 is exactly the link of delta 2 inside of delta. So if you intersect the link of delta 2 with delta, you get delta 1, and conversely. Okay. So now suppose I have blowups, x1 marked blowups for delta 1. And since they're U0 invariant, I can realize the action of F. What I mean by that is there's some restriction mapping to delta 1 or a delta 1. And I can, whatever that finite group is, suppose I can realize that by acting on this blow up for delta 1. And say I also have H2, X2, and H2 a blow up for delta 2. And both of these realize the restriction F. Well, it turns out that any blowup for delta is just the product of 2 blowups for delta 1 and delta 2, as you might guess. Or maybe not. So any blowup for delta is a product of blowups for delta 1 and delta 2. So then if I define x delta to be x1 cross x2, and I give it the product marking h1 cross h2, and then I let f act on here by the product action, then this will realize the f on this marked complex in this. Okay. So if you have a join and you know how to build it on the pieces, then you can blow up on the product. Okay, so that was one case. And the other case is if you have a disjoint union. And this is a little trickier. This is where we'll see some analog of the Karas-Piotrowski-Solitar result. So let's say delta now is a bunch of components, sigma 1 through sigma k, and then some set lambda. So I'll assume that delta and each of the sigma I are U0 invariant. And lambda is a collection of singletons. Okay, so in this case, what is a delta? It's a free product of each of these A sigma I's. And then there's some free part corresponding to lambda, maybe. And since these are U0 invariant, I get extensions of F, of each of these A special subgroups by the finite subgroup. So let me say, just to give them a name, we have extensions in the same way we made them for the free group for A delta. So I'm going to call that A delta hat and A sigma I hat. Okay, so these are the extensions by F restricted to each one of these groups. Oh, great. That's going to be recorded forever. Okay, so what do you need to prove? The following proposition. Let's say let X sigma I hi be marked blowups realizing F restricted to A sigma I. Okay, then there exists a marked blowup. Let's say X delta H realizing the restriction of F to A delta. Okay, and let me just say a sketch of the proof here. Yeah, okay. So we have this free product decomposition. And since each of these are U0 invariant, they're each preserved up to conjugacy. So this finite group is acting on this, but it's just taking each one of these factors to a conjugate of itself. And so in a previous paper, Hensel and Kulak proved a sort of relative version of the Karas-Piotrowski-Solitar result. And they show that that this extension A delta hat acts on a tree T such that so the vertex stabilizers are either finite or they are these conjugates maybe of these A sigma I hats, okay? And the edge stabilizers are finite. And so in particular, when you quotient by A delta, if you quotient this tree is a graph G, let's say of rank equal to the free part, this free part here, okay? So you get some graph And then each one of these sort of edges is labeled by one of the a sigma i's. Okay. And if we look up back in the tree, what we see are, let me maybe use some colors here. So if I take some vertex and say it's stabilized by a sigma I hat. So I have all these edges coming out, and each one of these edges corresponds to some finite subgroup, which acts on a sigma I. Let me just call that Fi is for the stabilizer of that. So, and so what you can do is then you want to expand this vertex into a copy of the universal cover for X sigma I. So the fixed vertex to X sigma I twiddle. Okay, so I can sort of, at the expense of overusing the word blow up, but blow up this vertex to a copy of the universal cover. And now you have this finite group acting on the universal cover, which is a cat0 cube complex. So there's some fixed point. And now I can attach that edge to the fixed point that I see there. Okay. And so you do that for all these edges coming in. And now you get a nice action, a proper co-compact action. So now this will be X delta twiddle. And now the point stabilizers are finite. And so, right, so if you take this X delta twiddle and mod out by A delta, that will be my X delta. It comes equipped with an action of A delta, and that's the equivalent to giving my marking, as in the case of the free group. Okay. So what does this thing look like? It's a tree of spaces. Yeah, exactly. It's a tree of spaces. So the quotient, it looks like you've taken all of your X sigma i's. I'm not going to get the same. Oh, I can try to get the same graph. So something like you have your X sigma I here. You've attached them in the same way along some edges now between these two, right? And yeah, so you haven't even changed the action on each of these pieces. It agrees with whatever it was before, but then you just connected them up with some edges. Whenever some of these edges might be in like the middle of a cube or something like that, and then you just have to subdivide to get a complex for this. And you can show that such a thing is a blow up, and essentially any blow up for X delta is also going to look like this. Okay, so in the same way that the join case we sort of is just a product, any blow up for a disjoint union is going to be look like this. Okay, so in the last 10 minutes or so, let me tell you how this factors into the sort of inductive scheme, which I think is a nice tool for understanding subgroups of U0. So we're going to consider chains, maximal length chains of U0 invariant subgraphs. This is a maximal chain of U0 invariant. And we'll induct on the length. So what's the base case? It turns out that any minimal U0 invariant subgraph is just a free group. Okay, so gamma 1 is always free. And so we can apply the Nielsen realization for free groups there, and we get this. And then at stage I, what you see is the following picture. So here's maybe gamma I. And then we're adding in some new stuff. So I'll call this theta. So theta equals gamma I plus 1 without gamma I. And it turns out that by maximality, every element of theta has this sort of common link in the previous thing. So everything here is joined to some subgraph of gamma I. And in general, there may be extra stuff in here. Maybe C, which is also the link of these things as well. So this is what you see. And now we can determine which of these are U0 invariant. Maybe I'll just go here, actually. So, right, so what's U0 invariant? Gamma I is U0 invariant. This is the link of theta intersected with gamma I, so phi is U0 invariant. And also this C is U0 invariant. Right, what else is there? There's lots of other things as well. I think I want to also say that C union theta is are U0 invariant. And so what we have are complexes for this, this, and this. And it turns out that you can arrange so that like this, the complex for C and phi actually sit inside of here as subcomplexes, sit inside of the, we have complexes already, X gamma I, we have X phi and X C. And these two sit inside of there as subcomplexes. Now, C union theta is a disjoint union. And I can apply the disjoint union case to come up with a complex for that. To come up with some complex X C union theta, and this X C will be a subcomplex of that. Okay. So now I want to build my new complex. Phi is a join, or phi it commutes with C union theta. So what I'm going to define is my X gamma I plus 1 is just X gamma I glued along X C cross X theta. So this already sits inside of here. And then with X C union theta cross X theta, X phi. Okay. And you can arrange that the action preserves each one of these pieces, the markings preserve these pieces, and so we actually get a marked complex, and then you just have to show that it's a blowup. Show that it's a blowup. And I'll say there's a, well, I mean, this is the tricky part. What the main sort of like issue that shows up is that not every blow up for one of these invariant things arises as a subcomplex of a blow up of gamma. So we have to make sure that our realization satisfy that property, which we call extendability. And it turns out you can always do it by possibly collapsing some subcomplex inside of it. But okay. Oh, I have some time. All right, great. Right, so that basically is the proof in the U0 case. But I just want to emphasize that I think this inductive scheme, what it allows you to do is sort of like if you know something's true for the free group, or you have some construction you want to do for the free group, and then you know how to sort of build it over joins and disjoint unions, then you can sort of cobble together blowups for bigger or more complicated things. But this only is for U0. So in the last little bit of time, maybe I'll tell you about how you might try to realize subgroups in out of A gamma in general. And this is something that we're working on. And sorry? No, actually, those are still annoying. Yeah, okay, so Yeah, maybe we can talk after about it. Yeah. No, this is about like adding twists is what I was thinking. Yeah. Okay, so the general. And I'm just going to tell you about a particular normal subgroup of the automorphism group, which is always there. So let me say, first of all, just quickly, we'll say that V is twist dominant if V is twist bigger than some U. So remember, this is when you have a twist, you can twist it onto some U. And then otherwise, we'll call it twist minimal. And similarly, we define if you actually have a twist, V goes to VW, this will be twist dominant if the thing you're acting on, the V, is twist dominant. And otherwise, we say it's twist minimal. And so there's this distinction between when you're twisting onto something that already can twist onto something else and when you can't. And this is an important distinction, but you can look at the subgroup, which is we call UTM, which is generated by U of A gamma and just all of the twist minimal twists. And it turns out that this is normal. This is always normal in out of A gamma. Okay, and essentially you have, let's see, so UTM, you have a map to out, and then you have the quotient is essentially what I'll call T delta, and these are the twist dominant twists. It's not quite true, but there's a way to arrange so that's true. And moreover, this splits. So these twist dominant twists sit back inside of out, so this thing splits. So we always get this decomposition of out of A gamma as a sort of semi-direct product of UTM and these twist dominant twists. Now the twist dominant twists really sit inside of GL. They live inside, they sort of act only on the Abelianization, and they actually have a sort of symmetric space or homogeneous space associated to them. And so we conjecture that there's a sort of map, a nice map, maybe a fibration from our outer space onto a homogeneous space, which I'll call Q gamma, which looks like something that classifies these things. So this is a homogeneous space associated to, well, associated to what? This is like the Z points in some linear group. And so then you can extend to R to some Lie group. So I can tell you more about this if you're interested in, but this is really saying that the outer space will look like essentially something that looks like outer space for a free group, it'll map to some space that looks like outer space for GL and Z, and the fibers will look like something that looks like outer space for a free group. So this is a really nice thing, and this we're going to hopefully use this to get an understanding of outer space and also its finite subgroups. And I'll stop there.
So right now we have realization for unconsidered automorphisms in the zero place movement in the Greek graph.
Yeah, I mean, yeah, I think I have some ideas about how to do it, but you have to like somehow. The problem is that if you go to graph automorphisms, these subgroups don't stay fixed anymore. But if you look at the orbit, then you have to be doing sort of the same thing on each piece. So that's it's like what you were saying. You have to make all the lengths in the orbit the same. So that's essentially what it is. So in the free product, you have to allow like everything is preserved up to conjugacy or permutations of the free factors. But there should be something like that. Yeah.
Are there lots of finite subgroups that are not already inside UA gamma?
Yeah.
Are they easy to construct?
Well, yeah, I mean, like, so certainly if you have some torus, so right, so what is this map going to be doing, or what is this thing doing? You're sort of like, there's all these abelian subgroups in your RAAG, and you look in the universal cover of this space, and you've got some cat-zero metric on it, and so there's going to be some flat associated to that thing, and there's some metric on the flat. And so this map is sort of recording the metrics on all of these different flats as long as they're sort of twist dominant in this sense. So there's lots of, any automorphisms of the torus that you can sort of build into acting on these flats and things like that. And that will be something that doesn't live in there, but it does sort of live in the twist part, this T delta, for example. But then you can, you have the semi-direct product decomposition, but that doesn't mean every group is a semi-direct product. It just means sort of like, there's sort of, they can be sort of diagonally embedded in here, but you can construct lots of things. Yeah.
Okay, we have no more questions. Just thank for your attention. Continue to that approach.